This is part 2 of 2 on the section entitled Relationships between Cardiac Output and Venous Return. Figure 4-28 is shown here. Under Part A, you can see the effect of positive inotropic agents, and in Part B, you can see the effect of negative inotropic agents on the cardiac and vascular function curves. The solid lines show the normal relationships, and the dashed lines show changes. The circle intersecting the dashed line shows the new steady-state operating point. Inotropic agents alter the cardiac function curve, which can be seen in Figure 4-28 on page 154. Recall that for positive inotropic agents, these will cause an increase in contractility for a given end diastolic volume, or right atrial pressure. Remember that right atrial pressure can be used as a surrogate for left ventricular end diastolic volume, because right atrial pressure is much easier to measure via central line or a central venous catheter. And negative inotropic agents would, in the opposite fashion, produce a decrease in contractility. The effect of a positive inotropic agent, for example wabane, digitalis, or digoxin, on the cardiac function curve is shown in Figure 4-28a. Positive inotropic agents produce an increase in contractility, an increase in stroke volume, and an increase in cardiac output for any level of right atrial pressure. Thus, the cardiac function curve shifts upward, but the vascular function curve is unaffected. The point of intersection, or the steady-state point of the two curves, now has shifted upward and to the left. In the new steady state, the cardiac output is increased, and the right atrial pressure is decreased. The decrease in right atrial pressure reflects the fact that more blood is ejected from the heart, that is, the left ventricle, on each beat, and as a result of the increased contractility and increased stroke volume. Figure 4-28b shows the effect of a negative inotropic agent. The effect is just the opposite of a positive inotropic agent. There's a decrease in contractility and a decrease in cardiac output for any level of right atrial pressure. The cardiac function curve shifts downward, and the vascular function curve is unchanged. In the new steady state, cardiac output is decreased, and the right atrial pressure would be increased. The right atrial pressure is increased because less blood is ejected from the heart on each beat, due to increased contractility and decreased stroke volume. This causes blood to back up to the right side of the heart, just like traffic. The right atrial pressure would then increase because the blood is not moving as quickly through the heart. Next, we'll discuss effects of changes in blood volume. Changes in blood volume alter the mean systemic pressure and thereby alter the vascular function curve, which is the red curve, as seen in Figure 4-29. The effects of increases in blood volume, for example, giving a patient a blood transfusion, are shown in Figure 4-29a on the left side. Increases in blood volume increase the stressed volume and therefore increase the mean systemic pressure. The mean systemic pressure is the point on the vascular function curve where the venous return equals 0. Increases in blood volume shift this intersection point to the right and therefore shift the curve to the right in a parallel manner. The shift is parallel because there is no accompanying change in total peripheral vascular resistance. Remember, TPR determines the slope of the red curve, which is the vascular function curve. In the new steady state, the cardiac and vascular function curves intersect at a new point at which cardiac output is increased and the right atrial pressure is also increased. The effects of decreases in blood volume, for example hemorrhage or severe bleeding, are shown in Figure 4-29b. The decrease in blood volume decreases the stressed volume and mean systemic pressure, which shifts the entire vascular function curve to the left in a parallel manner. In the new steady state, cardiac output is decreased, and the right atrial pressure is decreased as well. Changes in venous compliance produced effects similar to those produced by changes in blood volume. Decreases in venous compliance cause a shift of blood out of the unstressed volume and into the stressed volume and produce changes similar to those caused by increases in blood volume, which is a parallel shift of the entire venous curve to the right. Likewise, increases in venous compliance cause a shift of blood into the unstressed volume, which is the veins, and out of the stressed volume, which is the arteries. and produce changes similar to those caused by decreased blood volume or hemorrhage, which is a parallel shift to the left. This is seen in Part B. Figure 4-29 is shown here. On the left you can see the effects of increased blood volume, and on the right you can see the effects of decreased blood volume. The effects of the change in total peripheral vascular resistance will be discussed next. Changes in TPR reflect changes in the degree of constriction of the smooth muscle of arterioles. Remember, the peripheral arterioles are the resistance vessels. As the smooth muscle in these vessels relaxes, TPR will decrease. As the smooth muscle constricts, the TPR will increase. Changes in TPR alter the extent to which blood is held on the arterial side of the circulation, that is, in the stressed volume. Changes in TPR alter both arterial blood pressure and venous return to the heart. For example, an increase in TPR, by restricting the flow of blood out of the arteries, produces an increase in arterial blood pressure and concomitantly a decrease in venous return. The effects of changes in TPR on the cardiac and vascular function curves are therefore more complicated than those produced by changes in contractility or blood volume. Changes in TPR alter both curves, both the vascular curve and the cardiac function curve. The cardiac function curve changes because afterload, which is arterial blood pressure, changes, and the vascular function curve changes because venous return changes. This can be seen in Figure 4-30 on page 156. The effects of an increase in TPR, which is constriction of the arterioles, is shown in Figure 4-30A. The first change is an increase in TPR causes an increase in arterial pressure by holding blood in the arteries. This increase in arterial pressure produces an increase in afterload, which decreases cardiac output, and therefore the cardiac function curve shifts downward. This is the purple curve, and you can see that this whole curve shifts downward as a result of the increased afterload. The second effect is the increase in TPR produces a counterclockwise rotation of the vascular function curve. This rotation means that less blood returns to the heart for a given right atrial pressure. The venous return is decreased. And you can see that the red curve is shifted counterclockwise or to the left. But the mean systemic pressure, the point at which the red curve crosses the x-axis, is unchanged. The third effect is the combination of these two changes is shown in Figure 4-30A. The curves intersect at a new steady state point at which both cardiac output and venous return are decreased. The blue circle simply shifts downward in position. In the figure, the right atrial pressure is shown as unchanged, but actually, the effect of increased TPR on right atrial pressure is not easily predicted because TPR has different effects via the cardiac and vascular function curves. An increase in TPR decreases cardiac output, which increases the right atrial pressure, meaning less blood is pumped out of the heart, which causes a backup of blood into the right atrium. An increase in TPR decreases venous return. Remember that as resistance increases in arterioles, there will be less blood flow into the veins. Less blood flow into the veins from the arteries decreases the venous return back to the heart. This decreases the right atrial pressure. Again, less flow back to the heart. Depending on the relative magnitude of the effects on the cardiac and vascular function curve, the right atrial pressure in this situation could be slightly increased, slightly decreased, or unchanged. The figure that we have shows it as unchanged, the compromise position. The effects of a decrease in TPR, that is dilation of the arterial or smooth muscle, is shown in Figure 4-30B. Decreases in TPR cause a decrease in arterial pressure and a decrease in afterload. This causes the cardiac function curve to shift upward. There's more cardiac output available if the arterioles will relax their smooth muscle. The decrease in TPR produces also a clockwise rotation of the vascular function curve, or the red curve, which means that more blood returns to the heart for a given right atrial pressure. That is, venous return is increased. As you relax arterioles, the blood is able to move from the arteries into the veins more easily and then back to the heart. The curves intersect at a new steady state point at which both cardiac output and venous return are increased. However, the effect of decreased TPR, again on right atrial pressure, is not easily predicted because a change in the TPR has different effects via the cardiac and vascular function curves. A decrease in TPR increases cardiac output, which will decrease right atrial pressure because more blood is being pumped out of the heart and less blood is held up in the right atrium. Decrease in TPR increases venous return, which will also increase right atrial pressure. That is, more blood is flowing back to the heart. Depending on the relative magnitude of these effects, again, the right atrial pressure could be slightly increased, slightly decreased, or unchanged. In our figure, it is shown as unchanged. This is the end of part 2 of 2 in relationships between cardiac output and venous return.